Welcome to Energy Talks, a regular podcast series with expert discussions on power system testing topics. My name is Scott Williams from the podcast team at OMICRON, and I will be your host. Hello, everyone. In this episode, I talk with my guests about a new on-site measurement method to detect coupling and cable shields, which can cause overheating and damage to parallel medium voltage power cables. What led to the development of this new measurement method? Well, something that I always admire about OMICRON is that it has a strong commitment to helping customers get the most out of their power system testing equipment. It is a key part of the company culture to regularly and actively listen to customers to share with us their experiences in the field and to find ways to help them solve any problems they may be having. Sometimes additional measurement methods that did not exist before are developed by OMICRON to help customers solve frustrating power equipment issues they've been trying to figure out. One such example is when multiple customers were reporting an identical situation they have been experiencing with their parallel medium voltage cables. It turns out the coupling in the cable shields was causing overheating, which frequently damaged the cables. During the design stage of these cable systems, simulation techniques are used to estimate different scenarios, but up until now, no on-site measurement method was available during commissioning to measure coupling once the cables had been installed. This is how my two guests got involved in developing a new on-site test for coupling and cable shields. Joining me in this episode are Florian Fink, who is an OMICRON expert for the testing of industrial and distribution grid applications, as well as Moritz Pikisch, who is an OMICRON application expert for line and ground testing. Florian and Moritz described the situation that customers were experiencing with their parallel medium voltage cables, what causes coupling and cable shields, and how the coupling measurement they developed uses existing OMICRON power system testing equipment to reliably assess the situation during commissioning of medium voltage cables or when a problem is suspected later. Florian and Moritz, welcome to this episode of Energy Talks.
Hi, Scott. Great to be here.
Hi, Scott. Thanks for having us.
Thank you both for joining me for this discussion about your new method for testing coupling and cable shields. Florian, why are several cables used in parallel when transporting electrical power, for example, in medium voltage cable systems?
So the thing is, cables can't have square roots bigger than 500 square millimeters. That is already a very big cable. And if you need to transport higher currents, then you have to use multiple parallel cables. So applications are typically if you connect two substations with each other because you need to shift load flow from one to the other, or if you have a power plant after your generator, you have to bring power to a step-up transformer. And for these cables, you normally use parallel cables to transport the power.
Okay. Now, what are some of the design criteria that need to be considered when dimensioning cable sections for these systems?
Of course, you have the design criteria like normal when you're designing medium voltage cables. So, for example, the temperature is not getting too hot, or that the current is going in the right direction, or the voltage drop over the whole system. But as we will talk also about the magnetic fields, that's also a challenge that you have homogeneous magnetic fields, otherwise you get in troubles.
Okay. Now, what poses the biggest threat to these cable systems that can result in damage and costly repairs?
So we have been reported from multiple customers that they had issues with their cables. And here, for example, we had one customer where they had an industrial power plant, and in one point of time they had a ground fault on the cable. As these ground faults were, of course, inspected, and what they found out that the cables had really damaged, so you could see the shields of the cables were already showing out of the insulation of the cables, and the sand has bonded also with the insulation. So it seems that these cables have become very hot.
Now, what is the primary function of a cable shield, and why is it affected by coupling?
So the cable shield is for proper grounding. For example, if you have a fault on the cable, maybe from construction site, that you directly have proper grounding, that the fault current can flow over this cable shield. Or, of course, it has also the advantage if you connect assets or substations with each other, that you have proper grounding in between by these cable shields automatically.
Okay. Florian, how can this situation be best prevented?
Of course, in high voltage applications, you normally do cross bonding. So you have every several hundred meters a link box, yes. And in this link box, do a cross bonding. So you change the shields between the different cables, but that is normally too expensive to do that in medium voltage applications. So there it's not used. You can do also a single side grounding of medium voltage cables, but that has also some disadvantages.
Okay. Thank you, Florian. Moritz, what methods are currently available for determining the presence of coupling, and why are they not so ideal?
Well, one option you always have is simulation based on the design parameters of the cable. So basically the cross-section of the main conductor of the cable and actually the arrangement of the shield and the main conductor. And of course, as Florian already mentioned, the laying of the cable also has quite a huge impact on the coupling of the voltage into the shield based on the operational current. Of course, there is other parameters which play a role, like the soil resistivity, for example. And all these parameters are then actually taken into account for the simulation.
Okay. So I understand that you all developed a new measurement method to detect coupling and to make an assessment. What was the motivation for developing a new measurement method?
Well, the problem with the simulation is that you don't necessarily know all these parameters with a high accuracy. So whenever attempting to simulate the effect of coupling, your estimate or your simulation actually might be quite inaccurate. So we actually were rather thinking about directly measuring it, as we already do this with line impedance measurements and also ground testing. Will you also have the alternative of simulating what you actually also can measure directly? And our experience is that the measurement is more accurate, because you actually don't have to estimate parameters which you don't know accurately enough. Therefore, we were thinking about just doing the same there, right? So you actually just de-energize your test object, so your cable in this case, and inject the test current.
Or even better, you do it maybe before or during the commissioning, so you know the current over the shields already before you bring it into service, and then you can think about countermeasures if this is necessary.
Could you both describe the new coupling measurement method developed by OMICRON for assessing this situation? Which testing devices are used, and how does the method work?
Yeah, we're using the equipment CPC plus CU1, so the same equipment as for line impedance testing. And the first reason why we're doing this is safety. So this is a quite well-established test set, which has been used for now actually almost 20 years for safely injecting a test current into overhead lines and power cables, because it actually comes with a coupling unit. So the CU of the CU1 stands for coupling unit, and that's actually the first criterion we have to meet: safety, in order to ensure that the test engineer can operate the test equipment safely. And also it comes with an appropriate impedance matching for overhead lines and cables, in order to be able to inject an appropriate test current and also to measure correct test results or true test results.
Okay, very good. Now, I understand that there was a situation where you were experimenting with a single-phase power source and a three-phase scenario. Could you describe that process and how your proof of concept was able to show that the single-phase source was an ideal situation?
Yeah, so as Florian already mentioned, we actually wanted to know what the currents in the shields are for operational conditions, right? And operational conditions mean that we have a balanced current in the three phases of the cable. right? So here in this case, and as in most of the other examples in the power industry, we have a three-phase system, right? However, the situation is that the CPC plus CU1 is a single-phase source, and in order to actually reflect a three-phase scenario with a single-phase source, we actually had to use a little trick, right? So we actually inject the current or the single-phase current 3 times consecutively, one after the other. So we actually start injecting a current into phase 1, measure the currents with a current clamp across the shields in question. That do the same with phase 2, and do the same measurements actually across the same shields. And then again on phase 3, we also inject the current on phase 3 and then measure the same again. And then we can actually just sum up these currents. Of course, we also consider phase angle between the 3 phases. But the thing is, you actually get the response, and your response actually is the current measurement across the shields as is under real operational conditions, and actually treat your cable as a black box without knowing the properties of the whole system, which actually determine your coupling into your cables.
And the 3-phase measurement we did to prove just that the single-phase measurement is doing properly, bringing the same results.
Very good. So when you think about doing one measurement on all 3 phases versus separate measurements on each single phase, that takes a little bit more time. But why is that worth the effort, really? You had mentioned the benefits of it, that you were able to replicate similar situation and get the same results. But why, again, would you emphasize that the single-phase measurements work just as well, maybe even better?
I would not say better, but Moritz already mentioned the topic of safety, and the CPC plus C1 and the grounding unit is especially designed for that. So maybe coming to that topic, so we are working here in an environment which can be very dangerous. So we're working here on the cable where one side is grounded, and the side where we are injecting, we have to be sure that the whole system is safe enough for the person who is operating the measurement. Therefore, we are using the system of the CPC C1 and grounding unit, which is now, as Moritz said, known for 20 years doing these applications. So that's a very safe setup, which have been also proven in laboratories where they did some high short circuit tests. So maybe Moritz, you can go a little bit into the safety topic of this grounding unit.
Yeah, so the grounding box mainly actually is used to dissipate or to safely ground the local end of your cable, because as Florian already mentioned, the remote end of the cable is grounded. However, the local end of the cable needs to be ungrounded in order to be able to inject your test current. There is no other way to do this. So we're sort of violating a safety rule, if you want so. And as a result of this, we actually have to make sure that, or take additional precautions in order to be able to perform this measurement safely. And this grounding box actually is nothing else than a box with 3 surge arresters, which are protecting the device and therefore also the operator, the user of the device, in case a lethal voltage is actually getting or is occurring on the cable.
Okay.
So it's actually also designed for dissipating quite high currents, up to 30 kiloamps. So it could actually also dissipate the power of an energized cable, right? So in the worst case, what could happen in the worst case is that someone is removing ground from the remote end and energize the cable from the remote end. And even for this scenario, the grounding box would be designed and would be capable of safely diverting the energy to ground and protect test equipment and the user.
Very good. Okay. Now, what type of information were you able to generate from this type of measurement, and how was or is it better than a simulation?
Well, what we actually found out is actually the current which is flowing under certain load conditions. And I think what was surprising, Florian, correct me if I'm wrong, but actually it was quite surprising to learn and to see that such a high current is coupling into the shield, right? And which is actually something which needs to be considered, especially as the shield is not mandatorily designed for an arbitrary current which is coupled into the shields, right? So there was a pretty direct explanation of the development of a certain heat excess which actually damaged the cable.
So in this measurement Moritz mentioned, we had a cable system of 5 parallel cable systems for the length about 500 meters. The rated power was 23 MVA. So that means with this 6 kilovolts operating voltage, we had 2,300 amp nominal current. And what we measured, that when you have this nominal current of 2,300 amps, that would result into a coupling current into the shields of 70 amps. So for a cross-section of 35 square millimeter coupling shield, that would be already a high current, which brings an additional heating of the cable. And that, of course, can bring damages if it would be even higher when the installation would be not that optimal.
Okay, very good. So now you've had some experience in the field with this measurement, and you were able to prove that it's a successful measurement. When exactly should the test be performed, and how often? Now, you had mentioned it's ideal to do this during the commissioning of the cable system. Are there any other times when you would want to perform this test?
Yeah, of course. When you have doubts that you have at the moment problems with your medium voltage cable, or you have a bad gut feeling about your installation, or you have maybe already seen with the thermal camera that your terminations of the cables are getting hot, that are all indicators that you have maybe problems here. And then you can do such a measurement, which can be done in 1 to 2 hours, depending on how much parallel cables you have. And then you have a quick check. So it's normally nothing you have to do repeatedly, because that's a measurement which gives your information about your installation. So normally there is no drift or change in the system, but it gives you a very good indication about your installation.
Very good. So when you do notice overheating and a relation to coupling, what would be the action necessary to take? Would it involve a replacement of the cable, or what types of actions would need to be taken?
We've talked about that already earlier. I think cross-bounding in a box would be very tricky, because normally you have to do a construction site, and that would be very costly. You could think about single site grounded, but that comes also with some disadvantages, because, for example, you can't detect very well the ground fault from the protection anymore with a single site grounded. And you have to deal also, if you have a ground fault, with the site where you have no termination with high voltages. So you have to think about a surge arrestor. So there are some possibilities, but you have to think also of the second side of the medal, what comes with it.
Okay, very good. Thank you for that. Now, could you both summarize the importance of this measurement and how it can really save time in the end and help to avoid problems in cables due to coupling?
I think one important thing here is, if you do such a measurement, it takes maybe 1 to 2 hours more in the commissioning. But if you have damage on your cable system, that causes much more headache to the operator later on, because then you have an unplanned outage where you have to replace cables quickly. Often the cable is not only damaged on one location, it's the whole cable system what you have to exchange, and that creates costs and for the outage. And yeah, that's the thing why I would do such a measurement.
Moritz, we've been talking earlier about a situation where you have a cable system and you keep building around it after it has been installed, meaning you keep adding to the infrastructure it needs to supply. This can also create issues. Is that correct?
That is correct, yeah. So for example, if the infrastructure which is getting supplied by the cable is getting extended, this is something you definitely need to look into. And even if your cable from like a cross-sectional perspective can take the additional power, it's definitely worthwhile, as we have learned from this example, to look into the aspect of coupling into the shield. And if the additional amount of load and current is actually leading to heat excess, which might damage the cable with the additional infrastructure being connected and supplied by the cable.
And Scott, maybe one aspect which is not totally clear to the listener so far, the situation of this coupling into the shield is coming from the situation that we normally have in switch gears or transformers, the connection of the single phases A, B, C. And normally when you take a cable from a switchgear to another one, from a transformer to a switchgear, you try to bring your cables into the system that you always have. If you have 5 parallel systems with 3 phases, that you combine always one L2 and L3, and then normally, or in physics, the magnetic field is solving itself. But due to the fact that you come out of the switchgear or the transformer with the 3 phases where you have all the cables together, the magnetic field summarized even and couples on that area into the shield. And maybe Moritz, you can say also something about the length, what makes a change here to the system and the incoupling.
Yeah, as mentioned before, the laying of the cables also has an impact on the coupling into the shields, right? And so, as Florian already mentioned, you can actually lay your cables in a way that the fields are actually adding up across the shields, which means that there's actually a higher voltage resulting across the shield, and therefore in turn you also have higher current when grounding the shield on both ends. However, you can also lay your multiple 3-phase circuits in a way that the fields are actually canceling out each other's, at least partially, right? I mean, there will always be a certain field remaining, but at least you can mitigate the resulting field across the shield, and therefore also mitigate or lower the induced current across the shield.
Very good. So there's this word dimensioning in cable systems when you're laying cable systems out. This is exactly what that is. You're really calculating what the system can handle. Is that correct?
Yes. So that's a typical task of a design engineer, that he is thinking, okay, how much current I have to transport, or which voltage level, how much cables do I need, what are my circumstances, do I do during ground, or is it in a factory? So what are my surrounding conditions, what temperature I have normally, and that you can all bring into your calculation. But then also reality sometimes takes place. For example, if you have a switch gear, and under the switch gear there's not much space for do the cross section, then it could be that the cables are 1, 2, 3, 4 meters longer in parallel and not cross sectioned out, so that you have these incoupling effects. So of course, design is one thing, but practical installation is later another thing.
Okay, so this measurement is practically confirmation to the design calculations, right? When you're commissioning the system that you laid out, that you calculated before based upon anticipated load, you can use this measurement to really confirm that it's going to work the way you had envisioned it. Is that correct?
Confirmation and correction, if applicable, right? I mean, things always during the construction phase of cable, the one or the other thing might go a little different as planned, right,
sure,
and designed, right? So there is always a certain deviation between what has been planned and designed and actually what has been installed ultimately, right? And as I mentioned before, one of the big advantages of the measurement is that you actually measure your system as it is installed.
By the way, maybe an interesting fact, what we found out why we have written a paper about that topic. So if you're interested in further details, there's also in the OMICRON custom area a detailed paper describing the whole measurement, that the length of the cable or the parallel cables is not the biggest issue. It could be also that you have a short cable just of a few 10 meters can have already some problems. It must be not that this is a 500 meter installation like we measured here.
Could you describe this new testing method again for our listeners? What existing OMICRON devices are used and how is it performed?
Yeah, so we were using the CPC and the CU1 for the injection of the current, so pretty similar to the line impedance measurement. And so what we basically did is we were injecting current, the test current, into phase 1, and we were then measuring the currents in the shields, which have been coupled in by injecting this current into phase 1. Then we were doing the same on phase 2 again and also on phase 3, and then we were actually adding up the resulting currents in the shields in an Excel template in order to reflect operational three-phase balanced conditions in the cable, which you actually have during normal operational conditions.
Very good. And this was performed during the commissioning process of the cable system, and it took approximately 1 to 2 hours to perform. Is that correct?
That's correct, yeah. So this measurement you can perform during commissioning or when you have a bad gut feeling or you already have some overload or heated cables and you would like to find the root cause.
Florian and Moritz, thank you both very much for joining me and sharing your experience and insights into the topic of coupling on cable shields and the new testing method you developed for detecting it in advance.
Thank you, Scott. It was great to be here.
Thanks, Scott. Thanks for your interest. Thanks for hosting us.
Thanks again for being here for this discussion. And a big thank you to our audience for listening to this episode of Energy Talks. We always welcome your questions and feedback. Simply send us an email to podcast@omicronenergy.com. Also, if you like what you hear and have not done so already, please be sure to subscribe to Energy Talks on your favorite podcast platform to never miss an episode. OMICRON has several years of experience in power system testing and offers you the matching solution for your application. This includes innovative solutions for power cable testing and monitoring. For more information, be sure to visit our website at OMICRONenergy.com. There, be sure to look under Applications to find matching OMICRON solutions. Knowledge sharing is very important to OMICRON. On our website, you can also find the latest papers on various power system testing topics, upcoming seminars and events, as well as training courses. Please join us to listen to the next episode of Energy Talks. Goodbye for now, everyone.